All right, so today's plan is to just continue on with the chapter 4 PowerPoints, starting on part 2. I posted them in the chat a couple of times the last classes, and also they're available on the Blackboard site under supplemental material PowerPoints. And like I mentioned before, I'll have a supplement on chapter 4 posted later this week to make up for that missed class. I think it'll just be a little easier to maybe do that at the end of chapter 4 as opposed to the beginning of chapter 4. And the kind of quote of the day today, it's not a quote, it's actually, I decided to use this because it was a comic that I saw yesterday on Facebook. There's a I don't know, what do you call somebody who makes comics? Maybe they are a comic, I don't know. But an outlet called XKCD that makes these like funny comics with these stick figures, and we'll see another one or two of them later in the class. And I think we've already seen maybe one in a previous slideshow. But they came out with this one yesterday where one guy is saying when a metric becomes a target, it ceases to be a good metric. So if we're in a business and we want to do something with our business, we want to do some good in the world or bring some value to the economy, and we say, are we actually doing a good job of that? We might come up with a number that's a metric. But then what often happens is instead of us saying this number gives us an idea whether we think we're doing good or not, we start saying, instead of, hey, let's try to, do good even better, we say, let's try to make that number look better. So that's what they're talking about here. When the number becomes a target, it's no longer a good metric. It's no longer a good measurement of whether we're actually doing a good job. And then the other guy says, sounds bad. Let's offer a bonus to anyone who identifies a metric that has become a target. So, in the next week, they're probably going to identify 500 metrics that have become targets because they've chosen to incentivize finding metrics that have become targets. So it's a little bit silly, but there's some important components to this, I think, especially in stats. But really anytime that kind of data interacts with decision making. So in stats, you think of things like, for instance, machine learning and artificial intelligence, and we're starting to see that, maybe not starting to, maybe have seen for a while, that biases in the data set are reflected in the artificial intelligence. That's just hit the news again recently with a different AI tool. And so this is kind of what AI is AI is just completely numbers based, and it just says, okay, you told me to make this number really good, I'm going to do whatever I need to do to make that number really good. There's kind of I suppose kind of funny, also kind of scary YouTube video by a guy who works in AI safety named Robert Miles, and he talks about the stamp collecting robot and like how this robot will destroy all life on Earth because it can collect more stamps. And that's kind of how AI works. I mean, that's obviously hyperbole, but that's how AI works. Is it says, I have this one number, I'm speaking very roughly here, I have this one number, I want to make this number as large as possible or as small as possible or whatever, and I'll do anything that I need to make that number bigger. It doesn't have a moral compass or anything like that. But this also is a big issue in business. So you think anything from executive pay to incentive packages for employees. I have kind of a saying that I like to think about is whenever a company makes a person's job or their salary or their livelihood or dependent on a single number, people will destroy the business to make that number look good. So that's something that that I've thought about for quite a while. And when we set up incentive structures, we need to be very cognizant of that. When we're trying to say, okay, like, is this person doing a good job? If I just stick one number on them and say, if that number goes up, they're doing a good job. If it goes down, they're doing a bad job. And if I tie their salary or their bonus to that, I'm incentivizing them to make that number look good rather than to actually do a good job. I don't think there's an easy solution to that, because the plus side of a metric is it's very objective, and we, in a sense, want things to be very objective, especially when we're determining things like salary and so it's not an easy problem to overcome, but it's at least one to be aware of. Or another way to say it, a more kind of economics way, is that people respond to incentives, but perhaps not in the way you expect them to. So when you're creating an incentive structure, be really cognizant of what you're actually incentivizing the person to do. Are you incentivizing them to make a number look better, or are you incentivizing them to actually do a better job? And also ask yourself that, when you get into a career, like, what is my business incentivizing me to do? That might give you some insight into either their motivations or how much thought, time, and effort that they've put into the topic. Okay, so moving on to probability. We're just a quick reminder, we're in the probability side of things now, chapters 4, 5, and 6. This is the mathematical structure side of things. So we're actually, despite the meme of the day, we're actually moving away from the data side of things for the time being, and we're building up this structure that feels a little bit more like something like algebra or calculus than something like data science. So chapters 2 and 3, all about using data to understand the world a little better. 4, 5, 6, building up a mathematical structure, kind of looking at the problem from the opposite direction, at least for the time being, saying, if I knew everything about the world, what might happen on a single roll of the die, a single spin of the roulette wheel. And then in chapter 7 and 8, we're going to try to marry the two, and hopefully, sorry, and hopefully move into a situation where we can actually then make inferences based on the data, not just descriptions of the data set, but we can actually go outside the data set and make predictions, make claims about the world as a whole on the basis of some data. So that's what we're building up to. So 4, 5, and 6 is going to provide the necessary mathematical foundation for that. 2 and 3 provided some of the empirical foundation that we'll need for that. And then we'll bring the two together in chapters 7 and 8. Okay. This is the Isaac Newton quote that I referenced in last class's quote of the day. I won't read it again for you, but I kind of gave you an idea of what it said. And just kind of a fun little diversion for a couple minutes here. If we're thinking of probability, one of the places we use probability theory is in risk analysis. So if we say, what's the chance of getting in a car crash, or does it make sense to have insurance on the TV that I bought, those kind of things. So let's consider a couple of interesting questions. These are modeled after questions that a couple of guys, Kahneman and Tversky, asked back in probably between the late 60s and the 80s. They were, I would say, the founders of a field called behavioral economics, or closely related to behavioral finance. And that was kind of my area of interest in grad school. So trying to combine the kind of very rigid mathematical structures that some folks build mathematical finance on, but also realizing that especially over the last 30 or 40 years, there's a lot of psychology, a lot of human factors in the market. People get scared, people get greedy. That makes the market fluctuate more. 100 years ago, the average person didn't own stocks or bonds or any of that. It was mainly things like pension funds that owned those. And then the people were part of their company's pension, and the pension fund invested, and those investments were there to pay the folks who are part of their defined benefit pension program. But today we have mostly defined contribution programs where your company gives you some money essentially in an account, and you invest it, more or less however you want. And there's a lot more psychology in the market. So these guys, Kahneman and Tversky, kind of laid the groundwork for bringing together those solid, rigid mathematical structures that kind of assume everybody works like a robot, with some of the more human elements, fear, greed, some other things, the way that our brains work, which is very not robot-like. Okay, so let's suppose that you have a choice. Somebody walks up and they hold out two lottery tickets to you, and they say, you can pick one of the two. You don't have to pay me any money. You just pick one of the two. One is a ticket for a lottery where you have a 90% chance of winning $2,000, 10% chance of winning zero. The other is a ticket for a lottery with 45% chance of winning $4,000, 55% chance of zero. So think to yourself, which would you choose, A or B? Similar scenario, somebody walks up to you, I don't know why so many people are handing you lottery tickets today, but they are. Somebody else walks up and says, you can have one of these lottery tickets for free, lottery A or B. You can enter lottery A, where you win $2,000 with a probability of 0.002, or $0 with a probability of 0.998. Or you can enter lottery B, where you win $4,000 with a probability of 0.001, 0 with probability of 0.999. Which of these would you choose? And the interesting thing here is it's not necessarily true that, say, lottery A is better than lottery B or something like that. It's a question of how risk averse you are or how risk seeking you are. But if you choose A in the first one, you ought to choose A in the second one. And if you choose B in the first one, you ought to choose B in the second one. So if you're more risk seeking or more risk averse or whatever, that should carry through. But typically people will choose 1A and 2B. And this just kind of shows the psychology that in 1A, we look at 90% and we think, okay, basically I have a sure thing of $2,000, or I have a less than 50% chance of winning $4,000. Like, I'd feel like a goof if I opted for option B and essentially in my mind gave up $2,000 to try to win 4,000, and I'm going to lose more often than I'm going to win in lottery B. So I feel like a goof if I go to lottery B and I lose, and I could have had $2,000. In these lotteries, or in this lottery, in these two options, the thought process is more something like, well, 2 chances in 1,000 is like basically impossible, and 1 chance in 1,000 is like basically impossible. So why not go for the bigger money? Right? Like two chances in 1,000 of winning $2,000, and I wasn't going to win anyway. So why not try for 4,000? Of course, I mean, it's twice as likely that you win lottery A in this case and in this case. The ratios are the same. The decision criterion should be the same. But people usually aren't great at making judgments when there's a presence of extreme outliers, right? So something that happens 90% or 50-ish% of the time is much more tangible to us than something that happens a couple of times out of 1,000. So why do people make bad decisions when, you go and buy your car and they try to sell you an extended warranty or something, and you go and pay a whole bunch of money for a warranty with some goofball company that, might go out of business in 2 years anyway? Well, because number one, we don't have to make those decisions very often. And number two, well, maybe number two is we have the high pressure salesperson using, sales tactics that work very well, that are very effective. I was going to say good sales tactics, but good is maybe a moral word, but let's say effective sales tactics. And maybe number three is car crashes also, or things going wrong in our car also don't happen very often. So I don't have a good feel of, if the transmission goes out, how likely is that to happen? How bad is that going to be? How much is it going to cost? So when we're dealing with things that don't happen very often, it's tougher for us to make good decisions. When we're dealing with things that we do all the time, if we go to the store and, I look at the price of apples or something, I'm like, oh, wow, that's a lot more expensive than it was last week. Maybe I'll buy bananas this week instead or something, right? Or if I go to Wendy's and it's a busy time and all of a sudden my Wendy's 4 for $4 meal costs, $18 because they're doing some kind of crazy pricing thing these days. Maybe I go somewhere else. So So decisions we make all the time, we're usually pretty good at. And this ties into that subjective probability idea from part one. Decisions we make often, we're usually pretty good at. Decisions we don't make very often, or that are very outlier or kind of tail event type decisions, much more difficult for us to intuitively make a good decision. And those are the times that we, I think I would say, benefit the most from really digging into the facts, really digging into the numbers, the statistics, doing research, trying to drive down to a foundation where I can say, okay, what's a good decision here? Should I buy this car warranty or not? Or should I, should I work for this company or that company? Which job should I take? I think those are the decisions where thinking very mathematically, very statistically gives us a real edge. And then a different scenario, you can enter one of two lotteries. Lottery A, 80% chance of winning $4,000, 20% chance of zero. And lottery B, 100% chance of winning $3,000. And here, most people tend to choose B. Again, not that lottery A is better or lottery B is better, but lottery B on average yields more money than lottery A. We get a better return in a sense from lottery, sorry, I said that backwards. Lottery A is better than lottery B. Lottery B gives us $3,000, no ifs, ands, or buts. Lottery A, basically 4 times out of 5, we get $4,000. 1 time out of 5, we get 0. So if you thought of, having like 5 pieces of paper in a hat, 4 of them say 4,000 and 1 says 0. If I took those 5 data points and got X bar, right, that would be 4,000 times 4 lots of 4,000 divided by 5 for the number of data points. So 4,000 times 0.8, 4/5 is 3,200. So the risk or the volatility is also important. So it's not just the average that we're targeting. It's also something like variance, standard deviation, volatility, or maybe risk. In finance classes, a lot of times they equate risk to standard deviation. I think that's a particularly terrible practice. If somebody came up to you and said, here's a free, Powerball lottery ticket, would you like throw it on the ground and run away because it's so risky? Well, no, all of the volatility is on the upside. You might win $0 or you might win $1 billion or whatever, but so it's not, if all the volatility is on the upside, that's not what we call risk. It's really downside volatility we call risk, but that's kind of a side note. But if you're in finance classes, you might see them just say, oh, standard deviation, that's risk. I think that's ignoring what risk actually is. It's really volatility. But anyway, so risk or volatility is important. In this case, I use the term risk because people will look at this $3,000 sure thing and they'll basically say, they'll anchor on that and they'll say, like, I have $3,000 in my pocket. Am I willing to give that up to play lottery A? They'll basically say, am I willing to pay $3,000 to enter lottery A? And very few people are willing to do that. Maybe some, NFL star or somebody who makes a lot more money than any of us do. Maybe they don't really care about this, but for most of us, that's it's a little too much. I'm not going to pay $3,000 to gamble on maybe winning 4,000. So in this case, the volatility is on the downside, the chance of losing the $3,000. So Nassim Taleb from the Black Swan, the guy who the quote was from last time, he talks about, he actually made his money essentially investing in investments that were, for them to pay off, something so extreme would have to happen that everybody looks at it and says, oh, that just can't happen. Basically, what he did is he entered a lot of lotteries like this. And his counterparties, he would go into things like options or things like that, where there's a counterparty that you're basically drawing up a contract with. And the counterparty didn't see a difference between these two lotteries, essentially, or they were willing to sell him, this option with a 2 in 1,000 chance or this option with a 1 in 1,000 chance at the same price. They said, you're never going to win anyway. So pay me $5 for lottery A or pay me $5 for lottery B. I don't really care. But they neglected to actually break down and do the math and do the tough calculations and figure out what these were actually worth. He made a lot of money buying investments that almost always his purchase, his contract, he paid a premium, and almost always he lost all of his money. But on the investments that did pay off, because he paid so little for them, because people just were like, that's impossible, this is just free money, I don't care what you pay me for it. When he did make out, he made out huge. So maybe 1 in 100 investments would pay off, but when it paid off, it paid for all the others plus a whole lot more. Paid for all the losses plus a lot more. And that's why he named his book The Black Swan. He made his money and the money for his hedge fund and his investors by waiting for these black swan events, these quote impossible events that didn't fit in with somebody's mathematical model that they took as gospel instead of just an approximation. He just waited for a situation to arise where their model failed. And this is another little context here. Keep in mind, Kahneman and Tversky, 60s, 70s, something like that. So that's the social context here. This is another one of the Kahneman Tversky questions. So Linda's 31 years old. She's single, outspoken, very bright, majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Of the following two statements, which is more likely? That Linda's a bank teller, or that Linda's a bank teller and is active in the feminist movement? And almost everybody says the second option. And again, this is, just pointing out that that subjective probability, when we're using that, when we're using gut feelings, we can easily be deceived. Logically, it has to be true that Linda's a bank teller is the more likely of the two options. And the reason is that Linda's a bank teller and is active in a feminist movement. That's an additional qualification, right? If we think of say the Venn diagram over here, here's like the set of all people who match, I don't know, the set of all people, I don't know, or maybe all people who match that description. Some of those people are bank tellers. And then to be a bank teller and active in the feminist movement, that's a strict subset. Right. So there are going to be strictly fewer people who are bank tellers and active in the feminist movement than who are bank tellers and who may or may not be active in the feminist movement. So if there's even one person who fits the description, is a bank teller, but is not active in the feminist movement, it's strictly less than, but at most it could be equal to. So in probability, anytime that we stick an and qualifier on, we reduce the likelihood, because now for the event to be true, something has to be true and something else also has to be true. Okay, so just kind of one quick note that I mentioned here is that estimating the mean of a distribution, the kind of typical things that happen, is usually not too difficult of a problem. Estimating the tails of a distribution is a very difficult problem, and it's quite a difficult problem. It requires a lot of data, and if we have a whole bunch of data, there are some fields that can get a whole bunch of data, say like medicine, but often if we have a whole bunch of data, we also have issues of something like inconsistent units. Maybe it's from different time periods, different eras, different, there might be shifts in the time period over which that data was collected, or among the different populations from which it was collected, or whatever. Okay, so moving over, we talked about the addition rule last time. So moving over to the next rule, the multiplication rule. For the addition rule we had, so just to recap, The addition rule dealt with the conjunction or events that look like A or B. Roughly speaking, the or kind of just the probability distributed over or as plus, more or less. We were interested in whether two events are mutually exclusive. If they were mutually exclusive, we had this simpler form of the addition rule. If they were not mutually exclusive, there was some overlap, we would overcount the folks in the overlap, or the data points or the outcomes in the overlap, by one, because we count them with the A's and also count them with the B's. So we had to subtract off one of that overlap. So these were the 3 points for the addition rule. The multiplication rule is going to feel somewhat analogous. Just looking ahead a little bit, the multiplication rule is going to deal with the conjunction and. So looking at events like A and B, or like Linda's a bank teller and is active in the feminist movement. So that's why we discussed that bit from Kahneman and Tversky. Roughly speaking, the and kind of turns into a times, how or turns into a plus. If I have like probability of A and B equals probability of A times probability of B, something like that, if I multiply two probabilities together, but I know probabilities are between 0 and 1, if I multiply two numbers together that are between 0 and 1, they almost always get smaller. I mean, I suppose if the two numbers were equal to 1, then so if we had two events that were certain to happen, and I said, what's the probability that they both happen? Well, it's just still certain to happen. But if we're strictly between 0 and 1, we multiply probabilities together, they get smaller. If I multiply 3/4 by 3/4, that becomes 9/16. That's like in the ballpark of, say, 1/2. I went from like 75% down to just over a half. When I multiply probabilities together, the likelihood gets smaller. When I add probabilities together, because they're non-negative numbers, the total probability tends to get bigger, as long as one of them is not an impossible event. So when I have a compound event like A or B, I'm allowing more ways to become part of that compound event. When I have a compound event like A and B, I have more restrictions. It's harder to become part of that compound event. And the multiplication rule has an important question. We would like to know if two events are independent. So that's what we're going to address now. What does it mean for events to be independent? And then we'll develop a multiplication rule, a simplified one for independent events and a slightly less simple one for dependent events. So two events are called independent events if the fact that one occurs, or the knowledge that one occurs, does not affect the probability of the other occurring. So for instance, if I take a coin and I flip it one time, and then I flip it a second time, and my event A is getting heads on the first flip, and my event B is getting heads on the second flip. If I know that I got heads on the first flip of the coin, does it make it any more likely for me to succeed in event B, succeed in getting heads on the second flip? No, it doesn't seem like they would have any impact on one another. If I roll a die and then draw a card out of a deck of cards, getting a 6 on the die roll, then drawing a king, I don't think they're going to have any impact on one another. But an example of a set of two events that's not independent might be, say, rolling a die twice and saying the event is that the second roll, the number from the second roll, is bigger than the number from the first roll. And so maybe my, event A is like getting a 3 or larger on the first roll, and event B is like getting a number bigger than the first roll on the second roll. Well, if I succeed in event A, if I got a number 3 or larger on the first roll, that makes it harder to get a bigger number on the second roll. If I failed at event A, if I got a number less than 3, 1 or a 2, that makes it easier to get a higher number on the second roll. So we can see that those are dependent. There's the knowledge that I've succeeded in the event A, that I got a high number on the first roll, makes it harder to succeed, or makes it less likely to succeed in event B. Okay, so our multiplication rule for independent events. If two events are independent, then probability of A and B is the product of the probabilities. Remember, if we had two events that were mutually exclusive, if there was no outcome that's in both A and B, then the event, quote, A and B has no outcomes. It consists of the empty set. Its probability is 0. And we just have probability of A or B equals probability of A plus probability of B if we have mutually exclusive events. So in a sense, the probability operator distributes over or as a plus. Here we see that if we have independent events, the probability operator distributes over and as a multiplication. So what's the probability of rolling a 3 and picking a queen out of a deck of cards? 1 out of 13 of the values of the cards is a queen. So I think I mentioned that I'll go over some of the details of cards and things for those of you who aren't familiar with a standard deck of playing cards. I'll do that in the supplement, just kind of as an aside, but there are 13 values. So 2 through 10, Jack, Queen, King, and Ace. And Queen is one of those values. So the probability of rolling a 3 is 1/6. The probability of drawing a queen out of a deck of cards is 1 out of 13. These are independent events. Pretty clearly, rolling a 3 or not rolling a 3 on a die doesn't affect the likelihood of getting a queen out of a deck of cards. So the probability that I roll a 3 and get a queen out of a draw from a deck of cards is the product of those two probabilities. I see that 1/6 is maybe about 17%. 1/13 is maybe 17 or 7 or 8% or so, something like that. So 7 or 8% here, 17% there. 1.3% is a lot smaller than either of those, because relative to either of these, rolling a 3 or getting a queen, I've added another criterion. There might be a lot of times that I roll a 3, but I draw a 2 or I draw a king out of the deck. That doesn't satisfy the compound event 3 and queen. So anytime that I add an additional criterion, the likelihood of meeting that the criteria for that event decreases. As I ask here, what's the probability of rolling a number greater than 2, then rolling a number greater than the first number? The first thing we ask is, are these independent? And we note that they're not. Now, that doesn't mean that it's impossible to calculate this probability or something. We could, in theory, calculate the probability, but we just could not use our basic multiplication rule for independent events to do it. We'd have to do something a bit more complicated. So at this point, this problem can't be solved based on just our multiplication rule for independent events. And that's because the likelihood of getting a number greater than the first number does depend on whether we succeeded or failed on the first event, on the first roll. A question like, what's the probability it will snow today and the temperature will be less than 20 degrees Fahrenheit? If we think of this as two separate events, it could snow or not snow. It could be less than 20 Fahrenheit or greater than 20 Fahrenheit. These are clearly not independent events. If it's 70 out, like it has been for a lot of this week, it's probably not going to snow, right? If it's cold, it still might not snow. It might not snow and be 15 degrees out, but if there's 15 degrees out, there's at least kind of, it could snow. If it's 70 out, it's pretty much not guaranteed not to snow. So again, these are not independent. We can't use the multiplication rule for independent events here. We could not just take, the number of days that it snowed in the last couple of years divided by the number of days over which we evaluated that and say that's the probability of it snowing on a given day. Do the same with being less than 20 degrees Fahrenheit and just multiply those numbers together. We can't do that. And actually, there have been a lot of, maybe a lot is a bit of an overstatement, but there have been a non-trivial number of actually kind of tragic cases where expert witness kind of folks will come in and do statistics and present it to the jury in a jury trial, and somebody will be convicted on the basis of basically somebody assuming independence and multiplying a whole bunch of numbers together to get a really, really small number and say, oh, geez, the chance that this could have occurred just by chance, just by, happenstance is like, 1 in 10 billion or something like that. Like, this is absurd. This person has to be guilty or whatever, but they assumed independence when they ought not have. And I think one of the famous cases, I think the lady's name was Lucia de Burke, but there are a couple of them that are like this. So we can't just go start multiplying numbers together willy-nilly just because we have an and. We have to always ask, are the events independent or not? And I think with Lucia de Burke, like a couple of her kids just kind of randomly died, like SIDS kind of deals. And that was basically the argument. It's like, well, what's the chance that, a couple of her kids like would have both died that way? Something along those lines. We can actually generalize our multiplication rule for independent events. If we have more than 2 events, we can just, and if, importantly, again, if they're independent. So if knowing that A occurs doesn't affect the likelihood that B or C or any of the others occur, and knowing that B occurs doesn't affect any of the others, and knowing that C occurs doesn't, if none of them affect any of the others, then we can just turn all of the ands into timeses, roughly speaking. Note that we could have done this up here if we had a whole bunch of events that were all mutually exclusive, where no 2 events shared any outcome in common. We could say the probability of A or B or C or L2 or N is probability of A plus probability of B out to plus probability of N. I think we tend to use that one a little bit less often than this more generalized multiplication rule. Give me 1 sec here. Sorry, with the warm weather and rain and all of that, my allergies have decided that they think it's spring. So anyway, so we tend to use, I think, this more general multiplication rule, maybe a little more often than the more general addition rule, but the addition rule generalizes in a very similar way. So we can see a lot of analogs between the addition rule and multiplication rule. Be a little bit careful. Sometimes having analogs like this is nice because you already maybe understand one pattern and you can adapt those ideas to the other pattern. Sometimes it can be frustrating, though, because when you have 2 analogous things, it's easy to get, some components jumbled up. So you might think, wait, does that go with the addition rule or multiplication rule, right? Like, so sometimes you can get things jumbled up a little more easily. So writing them out like this, or even putting them in a grid or something, might be helpful for you to have that, readily accessible. And then you can look back and be like, oh, okay, addition rule relates to or to plus, it cares about mutually exclusive. Here's the roll, so at least until you get used to using both of these rules. But let's look at this example over here. We toss a coin 5 times, comes up heads or tails. And just like dice, if I say we roll a die, the default assumption is it's a 6-sided die. It has 6 faces labeled 1 through 6, and each face is equally likely. Same with a coin, heads or tails, each side equally likely. We toss a coin 5 times, so we have a sequence of 5 tosses, each of which could be head or tail. What's the probability we get at least one tail? Now, remember, when we have sequential things like this, we talked a decent bit about this related to die rolls, but the same idea applies here with coin flips. We want to make sure that we set up the sample space and the outcomes in such a way that things are equally likely. So I want a sequence of heads and tails. So my, maybe outcome 1 is like all heads. Maybe outcome, these are O's. Outcome 2 is 4 heads, then a tail. Maybe outcome 3 is 3 heads, tail, head, right? So we're being careful not to count these as the same outcome. If we had set up our outcomes as like outcome 1 is getting, 1 tail on 5 flips, and outcome 2 is getting 2 tails on 5 flips, well, I can see that there's, like, for instance, seemingly a bunch of ways to get, say, 1 tail on 5 flips, but maybe only one of these sequences that yields 0 tails on 5 flips. We have a similar problem that we had to the dice, where there was like 1-3 versus 3-1, but there wasn't a similar idea with, say, 1-1 versus 1-1. That's the same die roll. So we wouldn't have equally likely events. We're going to think of our outcomes as being sequences of heads and tails, ordered sequences. So what's the probability of getting at least 1 tail? It seems like there's going to be a lot of those, right? I could get 1 tail, 2, 3, 4, or 5 tails. And getting 1 tail, I could have, for instance, this first sequence or this second one, or the tail could be in this place or this place or this place. So it seems like there's 5 ways to get 1 tail. There's going to be a bunch more ways to get 2 tails. A tail could be in like places 1 and 2, or 1 and 3, or 1 and 4, or 1 and 5, or 2 and 3, or 2 and 4, 2, right? I really don't want to go through and count all of those. But I can leverage one of my previous probability rules, and I can say, wait, this is 1 minus probability of the complement. If I have an event getting at least 1 tail, getting 1 or more tails, its complement is getting 0 tails. This is a counting number. The smallest it can be is 0. It has to be an integer. And if it was 1 or more, it would be in the event. So the complementary event is 0 tails or no tails. So I can much more easily compute this by computing 1 minus the probability of getting no tails. Or in other words, 1 minus the probability of all heads. And there's actually kind of 2 ways I could think of what's the probability of getting all heads. One way is a little more of a brute force way. I could say, well, I could think of all heads as an event consisting of a single outcome from this list of sequences up here. There is this list of sequences that are equally likely, very important. There is 1 outcome that's in the event. And how many outcomes are there? Well, remember the die grid. If we had 2 dice, 6 by 6 grid would give me 6 times 6 or 36. If I did something similar for my heads and tails, say on flip 1 and flip 2, I see I would get 2 squared, or 2 times 2 different sequences for 2 flips of a coin. If I had a third flip, if I think of going along a third axis, kind of taking this grid and then copying it and putting another one behind it. So for the third flip, heads, then tails. This gives me 1, 2, 3, 4, 5, 6, 7, 8 cubes, or it gives me 2 cubed, or 8. There are 8 of these unique sequences for 3 flips of a coin. And maybe we see the pattern. I can't really go into the 4th dimension, but maybe we recognize the pattern. For 4 flips, I have 2 to the 4th sequences. For 5 flips, I have 2 to the 5th, or 32 unique sequences, unique outcomes. I could find the probability that way. That was a decent bit of work, though, right? That was kind of like the brute force, like what I often call the sledgehammer method. It's like, I know how to do this. I can just like whack it with a sledgehammer until the problem breaks. I got the answer. Is there a more elegant method? Is there another way to solve this problem that maybe in some situations would be less hassle, maybe in other situations would be a much more useful way to do it? I could also think of getting all heads as a compound event. Getting all heads means I had to get a head on flip 1. And it might be a little hard to read my handwriting here, but that's H on 1 for head on flip 1. And I had to get a head on flip 2. And I had to get a head on flip 3. And I had to get a head on flip 4. And I had to get a head on flip 5. I see this is really just 5 kind of smaller events connected to one another by ands. I also clearly see that these are independent events. If I know that I got a head on flip 1, does that affect my chances of getting a head on flip 4? Well, no. So this is probably